Thank you for turning into this video. Today, we will explore the application of linear algebra in economics. Let's begin with the topic of fitting. What's the meaning of fitting? In the previous class, we discussed the problem of finding the closest point on a line. Fitting essentially builds on the same idea. If we have a set of data points, say in 2 dimensions, such as the income and years of teaching experiences for all professors at Vanderbilt, and there are a lot of points, we aim to find a line that is, generally speaking, the closest to these points. In other words, we want to identify a line, looks like this one. Let's minimize the vertical distance between the line and these points. To illustrate it, it will look like this. And then we will get an equation for this line, like income equals beta 0, which is a constant, and beta 1, which is a coefficient, times years of teaching. And once we get this equation and this line, if we have a random point, such as for a professor who have 10 years of teaching experiences, we can estimate his income. And of course, this estimate may differ from the actual income, but we will explore how to construct this line and analyze the differences in the predictions later. So let me show the types of curve fittings. The first one is the line fitting. Just like its name, use the line to fit in this point. And we can see there is an outlier here. An outlier refers to a data point that is too far from the line of best fit. Here, the green line is the best fit line. And in research, it is important to investigate the reasons behind the presence of outliers and then decide whether to return or exclude these points. Then another type of curve fitting, which is polynomial fits. That means use the polynomial looks like this to fitting in this point. And I will give you an example later. There are also some other categories of curve fitting, such as the multiple linear regression fits. And the equation of this will look like here's a beta 0 is also the constant, and beta 1 is a coefficient for x, beta 2 is the coefficient for z, and it will look like this. And you can also add other random variables, such as w or something else. And here y is the outcome, like income, to estimate. And because we have more than one variables in the equation, though it causes multiple linear regression fit. We also have nonlinear curve fitting, so this is an example of Gauss fit, and also the implicit fitting and surface fitting. You can find some examples for these fittings on websites. So let's look at an example of polynomial fitting. Suppose we have 15 random points. First, we fit the data using a linear polynomial. So this one is the first order polynomial. It's just a strict line. As we And then we expand it to a quadratic polynomial. So this is the second order. You can see it's a curve. And as we continue to increase the degree of the polynomial and draw the corresponding graphs, so this one is the fifth order, and this one is the 10th and 100th. You can see the line becomes more curved and starts to cover more and more points. So here is a question. Is this a good thing? Actually, if our goal is simply to fit as many points as possible, the answer maybe seems to be yes. However, this leads to a problem called overfitting. So overfitting occurs when the model fits the training data very well, but performs poorly on new unseen data. Like if you have 50 new data and draw them here, and the old right line cannot properly estimate these new data points, and it will have a big estimate error between the old line and these new points. And additionally, in economics, it's often difficult to find a meaningful explanation for models involving extremely high degree terms, such as x to the power of 100. If we write down the notation for this, it will be like income equals beta 0 and beta 1 and x, where x just represents the years of teaching, to the power of 100. So actually we cannot explain why we use x to the power of 100. And usually we just use a linear fit, means the first order polynomial, to estimate. And we can say that with 1 unit increase of years of teaching and the income increase with beta 1,